Okay, so one of the most important concepts in calculus is of the use of the derivative to find extrema. So today we're going to talk a little bit about what we call the extreme value theorem, and hopefully you know already that the extrema are the maximum and minimum values of a function on an interval. But what I want to talk about today is the relationship of maximum and minimum on a closed interval and an open interval. So for this example, a closed interval 0, 1 and the line y equals 2x. If I graph this on a closed interval, what that means is at 0, 2x is 0, and when x is 1, 2x is 2. So it's a line. Okay. And so on this closed interval, it actually has an extrema, and that's what I want to point out. Even though it doesn't look like a high or low point of a curve, this is still the low point. Why? Because the interval is closed. So this function has on this interval has a minimum of 0, 0. And actually the minimum occurs when x equals 0 and the minimum is 0. And it has a maximum when x equals 1. And the maximum itself, maximum value is 2. That's important to know, that if I ask what the minimum value is, that you're telling me the y coordinate. Now, let's say we changed this to an open interval. On an open interval, what we would then say is, because these are open circles, this doesn't have extrema. They don't actually ever reach those points. Okay, so no matter what, if something is a closed interval, and closed interval means these are brackets here, there is going to be both a maximum and minimum. Has to be. It's guaranteed. However, on an open interval, it is not necessarily true. Okay, so one thing that I want to show you then is just kind of a couple pictures of some open and closed intervals to demonstrate this. Alright, so let's say I had A to B and it was a closed interval, we'll call it A to B, and I had a function that went something like this. Okay. So in this case, it's a closed interval, and it's guaranteed to be then possibly no, it is guaranteed to have a maximum and a minimum. So we look, and this is the maximum because it's the absolute highest point on the interval A to B. And in this case, this is not the minimum because there is another lower point. So this would be the minimum. Okay. The main thing that I want to point out here is that we are used to just finding these kinds of minimums, and what you're going to have to get in the habit of doing in this class is also always checking the endpoints, because on a closed interval the endpoint could also be a max or a minimum. So this would have a max up here, which happens to be the endpoint, and this would have a minimum down here. Okay. What if I changed this to be an open interval? Same kind of graph, A to B. So I'd have an open and an open. Okay. Hopefully what you can see is, just make sure you realize this is an open circle. So this is an open interval A to B. That the endpoints cannot be the max or min here, but there could possibly be other extrema within the interval, and this one does have a minimum. However, on a closed interval, there is no guaranteed max and minimum. So this one does not have a maximum. And then, what if I have a closed interval, something like this, and a discontinuous point. Okay, so kind of the same thing. Alright, so in this case, the maximum would be up here, and this, you can't see it, is not continuous there, so this point is no longer a minimum. So we wouldn't call it a minimum because it's not filled in there. Well, and this isn't the minimum either because it's higher than the point there. So basically, it's not continuous. Okay, so that brings up a good point. So now I'm going to go to the extreme value theorem. So basically, there's a couple things that have to be true in order to use it, and I hopefully demonstrated those to you. When you're checking today, I want you to make sure that you check for a couple of things. The extreme value theorem is only true if f is continuous, and so that last example I showed you did not have both a maximum and a minimum, and that was because the function was not continuous on the interval. Okay, so if you have a continuous function on a closed interval, these are two things that have to be true. Both of them have to be true. You need to check both. Then f has both a maximum and minimum on the interval. And the maximum or minimum, and I'm going to put here, could be an endpoint of the interval. Okay. All right, so then moving on, I'm going to just show you one more example of how you would find the possible extrema on this closed interval. Okay. So, extrema can either be relative or local or absolute, and really, I guess I'm really concerned about the absolute, the lowest point. So, if you would graph f of x equals x cubed plus 2x on the closed interval, negative 3, 1, approximate the extrema. So let's take a look at that a minute if I can find my graphing calculator. I wanted to pause it, but alright, so I'm going to put x cubed plus 2x squared on here. And we're only going to look on the interval negative 3 to 1. So I'm going to just maybe make this negative 4 to 2, just to kind of see what happens. And I'll make this negative 10 to 10. We might need to adjust that. Oops, I have a scatter plot in there. I'm going to take that off. Okay, so what I want to point out to you is that there are some absolute maxes and mins, and if we would sketch a picture of this graph, let's trace at negative 3 and see where we're at. Okay, so we have negative 3, 9. A rough sketch. And then it comes up, let's go to trace and go to 1 and see what the high point is, just so we see that. 1, 3. Okay. And then we have some locals. Like the minimum is actually, I know this is 0, 0 without even doing this. Okay. And let's find this maximum right here. Is negative 1 1/3, so negative 1 1/3, about 1.18. Okay, so something like this would be my sketch. Okay, so it happens on this one since it's a closed interval and it is continuous. It is guaranteed a maximum and a minimum. These are what we call local. This is a local minimum, and this is a local maximum. What I'm mostly concerned about is the absolute min and max, and the absolute min and max are actually the endpoints of the interval. Okay. So what does this have to do with calculus then? Well, really, I want to point out to you that you're going to eventually be doing this without the original graph. And we've talked about this already, but these maxes and minimums are the endpoints of the interval, and here is where the slope changes. And so we are going to be finding the zeros of the derivative, which we've already started. Which brings me then to my next point. What we call the zeros of the derivative, or undefined, and that's a good point, are critical numbers. And so this is pretty important definition in calculus, that you realize a critical number is an x value for which the derivative is 0 or undefined. And we have to include undefined because I'm going to point out for you in an absolute value curve, the derivative is undefined there, right? Because that is a sharp corner. But this is still considered a critical number because it can still be an extrema. This is actually still a minimum of the function. Okay, so let's say I was doing something like this, where I wanted to find the critical numbers. What I would do is I would find, first of all, where it's undefined. So I look at the function, and this is not going to have any undefined derivatives because it's a not exponential, it's a quartic function, so it's going to be some kind of a smooth curve. However, it might be beneficial to us to distribute this, I think, instead of trying to use product rule. That's what I would do anyways. This is x to the 4th minus 4x squared. Okay, so then let's try to take the derivative of that. Okay, and remember, to find critical numbers, we're trying to find where the derivative is undefined. We already talked about this is not undefined anywhere, or that it's 0. So I'm going to set this equal to 0 and try to find them. To do that, I'm going to factor out a 4x, and I'm left with x squared minus 2. So I set these things then both equal to 0. And then I would set x squared minus 2 equal to 0, x squared equals 2, x equals plus or minus root 2. So the critical numbers, okay, remember these are the x values, but critical numbers, there's 3 of them, are 0 and plus or minus root 2. Those are possible then extrema, okay? So these are only x values. Okay, so if I'm trying to find something on an interval, what I would have to do is check 2 things, the critical numbers and the endpoints. But I'm just going to ask for a critical point on these ones, okay? So if f of x equals sine x, where are the critical numbers on the graph? So we would be looking for where the derivative is 0 again. First of all, sine is continuous. There are no non-differential points on that. So the derivative would be cosine of x, and we are only looking on the interval 0 to pi, 0 to 2 pi. Okay. And the 0 then of cosine of x, in other words, where's the cosine of x equal to 0, is actually at the top and the bottom, and that is then at x equals pi halves, thinking of the unit circle, and x equals 3 pi halves. Okay? I want to point out to you, so this is the cosine. If we are looking at a sine graph, this is the sine graph now, okay? So here's 0, here's pi, here's 2 pi, here is pi halves, and here's 3 pi halves. What happens on the sine graph is, voila, a critical number, which is the 0, the derivative happens to be a maximum, and that is not a mistake. And the 3 pi halves happens to be a minimum. So the point of this is really actually quite an important concept in calculus, that without a graph, you can find maximums and minimums of the original function by finding the zeros, or the critical numbers of the function, which is the zeros of the derivative. And that's what we're going to practice doing. Okay, last example, and I know this is a long video, but you'll hopefully break it into a couple parts and have to look back for maybe some questions that you have. Basically, when you are finding absolute extrema on an interval, if the interval is closed, I'm going to give you some steps. Okay? The first step, so this is on a closed interval, is you're going to first find the critical numbers inside the interval. So we don't include the endpoints at this point because they're within the function. 2, you're going to evaluate f of each critical number I'll put in here. So if you find critical numbers, find the y value there. Then you're going to evaluate f at each endpoint. Why do we need to do this? Because we talked about how sometimes endpoints could still be the max or the min. So the possible max and mins, absolutes, are either critical numbers or the endpoints, and we need to test all of them. All right, let's take a look at this one, and I'm going to model the 3 steps. Okay, so how do I find the critical numbers on the interval -2 to 1? I am first going to find the derivative and set it equal to 0. That's how we find critical numbers. That would be 2x plus 2. Okay, where does this equal 0? If I move this around, or you can just obviously see it, the critical number here is at x equals -1. Okay. So, I think I did that right. 2x plus 2, right? All right. So, then I go through. X equals -1 is my critical number. I'm going to evaluate in the original function now what is f of -1, because it's a potential extrema. So I plug it in, I get -1 squared plus 2 times -1 minus 4. And I get 1 minus 2 minus 4. 1 minus 2 minus 4 would give me a -5. Okay. Alright, so then I have to evaluate f at each endpoint. So we're going to do f of -2 is -2 squared plus 2 times -2 minus 4. So I get 4 minus 4 minus 4. And I get a negative 4 for that. And finally, I put in 1. So I get 1 squared plus 2 times 1 minus 4. I'm going to circle these. Which is 1 plus 2 minus 4. Which is a negative 1. Okay. So, these are my possible absolute extrema. What's the lowest point? This one. So, the absolute min is negative 5. And it occurs at the point x equals negative 1. But the minimum itself is negative 5. That's the lowest point on this curve. And the absolute maximum is on this closed interval again, is negative 1, and it occurs at 1. Okay. Now, if you would look, notice I didn't even get my graphing calculator out once. But if you were to check this on your graphing calculator, and then let's take a look at x squared plus 2x minus 4, I hope you would see that that is true. Let's do the window. Let's make it negative 2 to 1, just so we can see it. Okay, I don't think I put that in right. I did not. X squared, there we go. Okay, so if I was filling this in, here we go. There's the endpoint, there's the endpoint. This is the maximum of that closed interval because it's the highest point, and this was the minimum. But we did that all using critical numbers and the endpoints of the interval. So that is the extreme value theorem. And tomorrow or Monday, we'll talk a little bit more about some more difficult applications of that.